Well, good morning to everyone again. In this new day, first of all, I would like to say thanks again for the assistance. Yesterday she was ill, and well, today is right again. Yeah, thank you very much to stay here. Well, as I mentioned yesterday, the first class of today is the ultra high temperature ceramics or UHTCs. Well, today typically during this week we have divided the day in three different presentations. Today there are only two. Probably for some of you is even better this time. But well, we'll talk about this ultra high temperature ceramics, and in the second one about the max phases. Okay, there are more or less new materials in ceramics. Just to remember, the first day on Monday we talked more or less about the idea of ceramics, how to locate them in the energy generation systems. On Tuesday we talk about the thermal barrier coatings or environmental barrier coatings. Then yesterday we talked about the ceramic matrix composites and CMCs. And today, as I mentioned, we talk about the ultra high temperature ceramics and max phases. And well, yesterday I will explain you in the next slide. Okay. But what are really the ultra high temperature ceramics? Okay, well, with this name is obviously that is for high temperature application. Well, if you analyze all the possible materials, there are more than 300 materials with melting point higher than 2000 degrees. But for some application, even this temperature is not enough. Okay, and then, as always, we want to go further. And we put more or less the limit in 3000 degrees. For 3000 degrees, there are just only few materials that can resist. Okay. If we look, even there are few metals that that they have higher or melting points above 3000 degrees. Okay, like rhenium or wolframium or other materials. But you cannot produce a material only based on rhenium, for example. Okay, it's a really expensive materials, and it's not possible. Okay, other family of materials are the oxide. We talked yesterday about the zirconia for the thermal barrier coatings. Okay, but well, there are other possibilities. Okay, but there are families here, these borides, carbides, and nitrides, that belongs to this ultra high temperature ceramics. Okay, this hafnium diboride, the zirconium diboride, that probably is the most famous material within this boride family, and also well, the tantalum diboride. Of course, in the carbide, yesterday we talked about the silicon carbide because it has really good properties, but there are other carbides with higher melting points. Even the tantalum carbide, as you see here, that has a melting point even higher than 3800 degrees, is the material with the highest melting point. Okay, and also nitrides. I think the first day we talked about the silicon nitride, but there are other materials that even has higher melting point. Okay, I just plot this table here because most of them are not used alone. Typically, it's a composite of these materials, like we talked yesterday, to combine different properties. And when we combine them, we should take care because, well, normally when you combine materials, they can react, and you should looking for the eutectic point, of course, if we want to put these materials in high temperature. And then, well, depending materials, you should analyze with the possible reaction with other materials, especially, for example, with the silicon carbide, because many of these materials are reinforced with silicon carbide fibers, like we talked yesterday. But even with that, these eutectic points are at really high temperature, and as you see here, most of them are higher than 2000 degrees. I would like to give you or to provide you some definition of ultra high temperature ceramics, but there is not any definition. I mean, it's only the people give different possibilities, and in general, it's possible to say that there are ceramics materials with melting point higher than 3000 degrees, but these 3000 degrees totally randomly number. Could be higher or could be lower, and it's not a clear criteria how we can differentiate these ultra high temperature ceramics. Okay, the people is always talking about other researchers, but well, they stabilize this number, but could be even higher. Okay, and well, as I mentioned, mainly there are within these ultra high temperature ceramics three kind of family materials: the borides with the zirconium diboride and the hafnium diboride that are the most famous. In the case of the carbide, the most used is the tantalum carbide, and the nitrides, well, it's the hafnium nitride, the most explored, but to be honest, nitrides are not really well investigated, this hafnium nitride, for example, or other nitrides. Well, as you see here, in borides, in carbides, and nitrides, all of them has always the hafnium. Well, the materials by itself, it has a really good properties, okay? But hafnium has a really big problem in its really high cost. I mean, it's really expensive. And then, okay, if we want to do it in a lab scale, okay, maybe you can assume this price, but to generate really large pieces, as I will show you, for really components for the next generation of aero vehicles, well, hafnium could be a problem, even when it has a good properties. For that, typically the most uses is with the zirconium, in this case the zirconium diboride or zirconium carbide, the most uses, okay? Well, other problems, because of course if not these materials are perfect, they can resist really high temperatures as you see here, but it's always the problem, as we talked during these days, about the atmosphere condition. Of course the melting point is so high, but these ultra high temperature ceramics react with the oxygen, okay? Then we should protect them or do different things, okay? And well, here just to mention, because the NASA is working in that materials from a few years ago or decades, because they are really interested in the properties of these materials, but there are some gaps. To have idea, well, here in Spain, I think there is just one group in Extremadura working with that material, mainly in the sintering, Professor Zamora. Other group in London that I know, and of course in Europe there are a few groups that are working on that, but not many people is working on. Well, the same in USA, several groups, but there are not enough. And NASA is asking for several questions to the to the community in general, okay? And here, for example, I want to plot this table that is like the select recommendations that did a few years ago in the future research the NASA, if let's say if the community can help, okay? They ask, okay, if you can help us with different problems. For example, they are really interested in these materials due to the high melting points. In that here, that is TPS, that is thermal protection systems, okay? Because they want to use it, well, here, fortunately, also in rockets, but for the when the aerospace vehicles go out and came in the Earth, okay, for missions to satellites, or if we want to go in the future to Mars, okay? And then, well, they are looking for these kind of materials, and they think that these ultra high temperature ceramics can work, but of course, there are a lot of things that should be investigated, of course. Other thing is that obviously they are thinking in this kind of materials for extreme temperatures, okay, and then should be analyzed all the thermal and other pertinent material properties under these conditions, okay. And well, this list is only one part. It continues, but well, as you see, it's a field that there are a lot of road to do, okay. And here, well, the application and what is the potential of these materials. There is a gap for a really high temperature materials under extreme conditions or extreme environments, and probably the ultra high temperature ceramics are the most promising, with also the combination of the materials that we talked yesterday, the composites, in particular the silicon carbide, but if we want to go further, we need new ideas, and this is one of the possibilities. But the problem is that it's not only the really high temperature or the extreme environments. You should combine with also the reactivity, a lot of mechanical stress, radiation, of course, and the wear. I mean, there are a lot of things that should be improved. The main field for these materials, the hypersonic application, okay, for different vehicles that I don't know if in the future they will look like that, but okay, at least they are looking in that direction. The idea is certainly to control this one. As you see, all these vehicles, they have a really sharp edge, okay? This is to control the aerodynamic when they can enter in the atmospheres and so on. Up to now, they are more like with less sharp edge. I don't know if I have some pictures, no, but maybe in the next slides. And then they cannot control the angle when they enter in the earth, okay? And for this hypersonic application is really critical. And then the only possibility is to have materials with high thermal conductivity and with high melting points, because of course in that sharp edge they will suffer a lot of heat, okay? Another really interesting application is the nuclear one, that maybe the researcher from the CMAT is interested in that materials for that. They are already using these materials in the construction of the next generation of nuclear reaction, that is called Generation 4. I hope that this information is right for you. Well, I did a stay for 6 months in London with probably one of the best researchers in that field, that is Professor Lee, and they have several people working on that with the ultra high temperature ceramics. And well, sometimes they cannot tell us all the information because it's confidential, but yeah, they have really nice facilities outside London, because of course it's nuclear things. But yeah, to be honest, even I think they will be first in this nuclear application that in the hypersonic application, these materials. Then if you are interested, well, you can ask me, and even I can put you in contact, because well, in this presentation I will not talk about the nuclear activities because I have no idea, but I know that they are using on that. And of course, other applications, always that we talk about materials that can resist high temperature and the reactivity is low, as usual, to contain the molten metals, or for high temperature electrodes, or like the wear or the tribological properties of this material is good for some coatings to protect materials or this kind of thing. But in general, these two fields is the most promising. Okay. Well, first I would like to show you how they are formed, and then we will pass through the properties. The idea is to give you a overview. Okay. Then these borides or carbides, but in general, always that we talk about ultra high temperature ceramics are based in the diborides because it's the more used and also with the best properties. You cannot observe in the nature. Okay, you cannot go to a mine, do mining, and through different treatments obtain your material. You should synthesize. Okay, and then normally there are two possibilities. You have your metal, for example, zirconium, or the zirconium hydroxide, and combined with a boron source. Could be boria or could be other source. Okay, through reactive sintering, you can obtain at the end your dense material or porous materials or juboride. Other possibility, of course, first to do the synthesis or your powder, you obtain your powder and then the sintering. Okay, this is just fast. You do the synthesis and the sintering in one step, and here first the synthesis and then the sintering. Okay, What happened normally with the zircon diboride? As I told you, well, most of them at the end are oxidized, okay? Then you have your material that after, through the oxidation or the ablation for the really high temperatures or erosion, are deoxidized, and again the boron source. Then we can do this cycle several times, also for the fabrication through the application, okay? The transitions metal oxides that are typically used or formed here, because also they can be used for the synthesis. Well, obviously the oxide, like for example the zirconia or the hafnium oxide, okay? Obviously this metal should be the zirconium or the example for example. Regarding the boron source, the most typical is the boria, okay, or oxide or boron oxide, that is called boria, or this carbon boride, okay. And well, here in more detail, because we will go in detail of all these steps. If we start from our metal, we'll combine directly with borio, for example, with silica to do with silicon carbide to do the reactive sintering, or through other routes, okay, to obtain our ceramic. If we start from the oxide, that I think is more used in regarding the companies, I think so this one is more for lab scales. Well, you can do different kind of reactions, elemental reaction, thermal reaction, or different reductions of your material in order to modify the metal and have your powder, and at the end you will sinter in your material. Typically, as I mentioned, should be a composite, because we want to combine properties, okay? Fracture toughness of these materials are relatively low, and then it should be improved if we want to use it. And well, here, for example, to be honest, we are here in the reactive process for wood. In the case of the diborides, can be synthesized from 3 different reactions, okay? The first one, as is obvious, is by the elemental reaction. You have, for example, your metal and your boron source, and do the reaction. That, for example, is this one, even I think, yeah, I'll show you one by one, okay? Other possibility is the reduction process using oxide, okay? You reduce your material, and of course will be remove the oxygen and change by the boron. And the third one is, as I mentioned yesterday, and it's quite interesting if we want to produce large pieces, is to use chemical routes for polymer precursors, because with these polymer precursors we can do different treatments, and well, we can do infiltration or other different steps to produce complex shapes, okay? And well, here I put you a table with all the reactions, but I will go now to explain one by one, okay? For the elemental reaction, well, this is the easiest process, okay? It's quite simple. You just put, for example, your zirconium and your boron, and obviously through the reaction you will have your problem. However, as you see here, okay, the free enthalpy, the Gibbs energy, is negative. Probably you already know what does it mean. As I always told you, you can interrupt me or whatever you want, okay? But you know perfectly what is this, even probably better than me that are in the university, okay? Then this reaction is highly exothermic, and when you start to produce it, the energy is produced by itself, okay? But then you should take care, because if you do that one even in a lab scale, it can start the ignition, okay? Because the energy that it liberates is quite high. Then sometimes, if you want to produce a large quantity of this material, this heat can promote the melting even of one of the boron or the zirconium, that at the same time accelerate the synthesis process. The good part is, due to this really fast heating, because yeah, it's the enthalpy as is the reaction, the final powder will have a really high defect of concentration, and this will help the sintering step. I don't know if you remember on Monday when we talked about the defects in this thin oxide that we sintering at 400 degrees, and we thought that could be related with the defects, and we were investigated about that. Well, in this case, it's always related the best densification of this powder to do the FET concentration. Okay. The second process, and this one is I think is most used, is the carbothermal reduction. Okay. Here, well, the enthalpy is positive, then we should increase the temperature, and the reaction, for example, if we start with our zirconium oxide, we incorporate the boria and also carbon. Always then we incorporate boria, we should add exthet. I don't know if you remember from yesterday, but I told you, and in this class, hopefully it will be clear. Boria melts at low temperature, okay, and then it will be evaporated. If you want to do this reaction, of course, the boria at high temperature will melt, but after that will start to evaporate. Then, typically, always that you add boria in your system, you should add exthet of the content. Typically, for example, for these cases, is between 10 and 30%. It's in order to compensate the loss that you will have, okay, during the treatment. Other important thing is the carbon that you add. Depending of this carbon, that also can be stoichiometrically or even less or higher, will be depend the number of the carbon, because it reacts between also with the boria. However, and coming back to this excess of boria, this is critical. For example, just here to mention, no, if you add a really large amount of boria in order to react with this carbon, because we don't want this carbon in the final particles, well, of course, we'll generate a really nice zirconium diboride particles without carbon. This is perfect because carbon as impurity is a really bad material in our last dense component, but obviously it's not economical. Then again, if you are in a lab, okay, maybe it works for your investigation, but if we want to transfer really for companies, this is not the best solution, okay? And well, continue about this reduction process, because there are many possibilities. This one was called a carbothermal reduction, obviously because we add carbon. In that case, we do the carbon and also the borothermal reduction. In that case, was the oxide, the source of borium, but in this case, it's a carbide. Then one that we do is the reduction of the oxide using carbon and the boron carbide. Okay. Again, the free energy is positive when we should put energy to produce these reactions. Well, I don't want to put all the intermediate products, but there are many, and obviously we don't want these products in the final material. We want to obtain the higher purity as possible in our material. And well, here are the reactions at what temperature it happens, but okay, just to have idea, it's around 1500 degrees is when they start to promote the formation of the zirconium diboride. The good part, obviously, well, I think I don't need to mention, but well, there are the second product, but like it's a gas. I mean, it's removed from your powder. And well, just to mention here, always all the examples for these oxides is with the zirconium oxide, but it's absolutely the same process. For example, for the hafnium diboride or other diborides. Okay. More reduction processes. Now the borothermal reduction, we just use elemental boron. Again, free gives energy is positive, and then well, we should supply all this energy. Okay, but as you see here, this is the best method to avoid carbon. For one really easy question, is not carbon, then it's quite complicated. That at the end we have carbon, and this carbon, as I told you, is critical in the final material. Okay. But like always that I thought with you, you find one solution to one problem, this carbon, but then you obtain other problem. And here the problem is the oxygen. Okay, this I don't know if you remember, but during these days I told you, for example, if you have zirconium diboride, always the surface of your material are oxidized. Then it's always oxide in your material, or even zirconia oxide, or even boria as impurity. Okay, even when it's practically impossible to have a really pure material. And when this process, then there are more boria. Okay, it can be eliminate this boria because it melts, and after to pass to the gases state at this temperature, but then your particle growth, and then will be more difficult to sinter them. Okay. Other example, but are based in the same reduction using boron carbide. Just improvement. For example, here there are less contamination in carbon, or low contamination, because now again we put low carbon, but well, this one then maybe is better you improve in that way because are lower temperatures. Okay. But just to pass to other thing is about this reactive sintering process. Okay, they are directly here. Yeah? This one has one advantage. We were talking how to process the powder, then we do the synthesis process, use energy to do it, and then we will do the sintering. The sintering of these materials require really high temperature. So, for example, zirconium diboride requires temperatures around 2000, and you need to apply pressure. If not, it's not dense, and then you need to use or hot press, or hot isostatic press, or spark plasma sintering. Okay, and then with this reactive sintering, we save one step, because we do the synthesis and the densification in just one step. Then you save a lot of energy. This is the advantage, that you can produce already your dense ceramic just from high purity powders. Okay. Advantage, well, this one of course is just in one step, and through the reactivity you can obtain your dense materials at lower temperature, even lower than 1800 degrees C. Okay. Problems as with the reactivity process, the reaction are really exothermic. For that, even we can produce it at less temperature, but then yeah, you should take care, because even it can start the ignition of your powder. Okay. Yeah, that I put here is something that you should take care, but you can use it. Through this ignition process, you can produce a unique microstructure of your materials. Okay. And well, obviously, as I put here, you can control the densification and produce different microstructures. Okay. And well, I think I barely introduced that one, but really, if we are thinking in applications, probably your zirconium diboride or metal boride will be always in combination with silicon carbide. Okay. Later I will show you the properties, but the oxidation resistance is much better when you introduce silicon carbide, and also your properties. Then, well, if you are looking really for applications, probably all the people is working with that material. And here is to put you an example about how to produce by reactive sintering already your composites. Okay, and it's through the reactivity using hot press, of course under vacuum, like always in hot press, or well in argon in an inner atmosphere at this temperature for 1 hour. To start, we will start with our zirconium or silicon and the boron carbide. Okay, and then through the reaction we have our silicon particles that of course will be oxidized on the surface with silica or carbon for the reduction, and or probably bigger zirconium particles. Okay, and at the end, through the reactivity, we'll have our zirconium diboride here and our small silicon particles there. Typically, as I put you here, of course it depends on the densification, on the synthesis and densification temperature and process, if you are hot press or hot isostatic press, but in general they present as small grains, like around, even for the zirconium diboride I think it's a little bit higher than 10 microns, but for the silicon carbide it's less than 10 microns, and of course with that we will improve the mechanical properties. That normally, if you want to increase your mechanical properties, you should go to long grade growth. Okay. And well, just to put the example, for example, here if you use instead the hot press, you use spark plasma sintering, the final grain growth or the final particle size is even low than 5 microns, okay? Due to the, what I hope you learned during this day, that the SPS leads to really high heating rates, and then you can control more your microstructure. And well, here other possibility, because as always we want to go further. Just we want only the zirconium diboride and the silicon carbide particles. We also want to incorporate some carbides, for example, in order to increase the, in that case, for example, the tribological properties, combine different materials, and well, it's possible to do it through different reactions. Okay, here, as I try also to tell you that now are in the university, just useful thing. I mean, whatever you want to do, think hard, and okay, maybe nobody do it, but if you have in mind different reactions and things that can work, and or you want to incorporate other particles, just think, because probably it's possible to do it. Okay, and again, this one, if you do hot press or reactive hot press, you obtain a coarse microstructure, of course. If you do in a SPS, will be finer microstructure. Okay, again, for the short sintering times. And here, yeah, okay, perfect. Here is the example, okay, about these reactions, and as you see here, how they grow the elongate particles that correspond with the zirconium diboride or these silicon carbide particles, okay, these different phases. And as I mentioned, and it's here exactly that, leads to multiple possibilities. I mean, just think about that, what is exactly that you want, and probably you can process through different reactions, okay? And well, obviously, as normally happens always, this microstructure and therefore your final properties can be tailored if you think in different parameters, not only the maximal temperature or the heating rate that you use, also the particle shapes that you use, or the purity of your powders, or different things. Yeah. And well, here more information. Don't worry, we'll pass in a bit for the properties. But just to mention, the sintering of these materials, densification of this material is quite hard. Okay, they have excellent properties by these strovalent covalent bonds, but then at the end that you have is a really low diffusion rates, and then the densification is quite hard. If you try to densify these materials by pressureless sintering, just introducing a furnace, it's quite difficult, okay, quite difficult. And again, like always at least in ceramics, a lot of things, for not say everything, is controlled by the surface chemistry. I think I mentioned, but your zirconium diboride is always, well, let's say protect or passivate by the oxide layer, but also by the, if it's boride, by this boria, the oxide of the borium, okay? And then, yeah, this is critical. This oxide, the boria, at the beginning promotes the densification, okay? Because it melts, and you produce that is called liquid phase sintering, okay? Due to you surrounded all your particles with a liquid, there are capillarity forces that helps to the compansion, and also help the diffusivity between particles, because between them, when it's contact solid, it's really low, but if you put a bridge of liquid between, the transfer is better. But okay, this boria melts and helps the densification, but we have other oxides that will be present on the surface of our particles, that as you see, if you will remember, these oxides, well, just to really come back, some of them are here, for example, the zirconia or others. The melting point is really high, and then you will not melt, okay? And then they will hinder the densification of your material. It's like blocking the densification, and for that reason, you need a really high temperature. For that, typically, this sintering temperature is about 2000 degrees, okay? And always assisted by pressure. It's totally required. Obviously, these temperatures you cannot achieve in a conventional furnace, okay? You should go for a specific technique. The typical one is the hot press, but well, now that time by time the SPS is also used by the industry for different companies, they can be also performed. Okay, well, and it's here that exactly these two techniques that we talked, this SPS that I think we have talked enough during this day, and the hot presses, that this is more commercial than the SPS. And well, how we can solve this problem? As always, we find the problem and we try to find a solution or a strategy how to do it. Okay. Well, one of the best methods, and this Spanish group in Extremadura is working so hard in that one. The best thing if you trying to obtain the highest purity as possible in your powder, and also go, if it's possible, into the nanoscale. Okay. Of course, if you reduce the size of your starting particle, there are more energy on the surface, and then the reactivity starts at lower temperature, and the reactivity is easier. Okay, and obviously the purity due to the oxidation that I talked. And well, to do that, because as we mentioned, to obtain the nanopowder is quite hard directly, then normally you should do some mechanical activations, with the consequent problems that always that you put a step, especially milling, you introduce impurities in your material. Okay, but on the other hand, as you see here, it increases the defect concentration and it helps the densification. Okay, well, here also the people is working with this reactive synthesis in solid precursors. As I comment these days, the solid precursors are quite interested if we want, for example, to do some infiltration techniques or others. And one method that obviously is extensively used is to use sintering additives. Okay, we can add metals, nitrites, the silicides that are really typical, other materials, and also the silicon carbide. But with that, you should take care, because of course everything that you add in your starting powder, you will have probably in your final material. And well, it's like the silicon that we talk with the silicon carbide. At the end, it will be a problem, okay, at high temperature. But for that, this one is the material most used, because silicon carbide helps the densification, but also the final properties of the materials. And what? Here, just a few examples about these sintering additives that we talk here. One possibility to reduce the sintering temperature. As you see the content, well, here is 15, but I think it's quite hard. Normally it's less than 10%. Of course you can add it, but typically it's less than 10%. And then, well, at least you reduce a bit the temperature, okay, for the maximal densification. Normally, obviously, if you add, for example, 10% or 15%, you can reduce more the temperature, but then you should take care, because it will be in your final material. And one here also example for the hafnium diboride, but in terms of companies or to produce large pieces, as I mentioned, the zirconium diboride is the most interesting material. Here I mentioned that typically you should add pressure, okay, if you want to densify these values. Yeah, exactly, it's here. It's typically for hot press, because normally the ultra high temperature ceramics are densified in the hot press, but this to have idea, this temperature should increase around 100 or 150 if you use pressureless sintering, then we go at really high temperatures. Or on the other hand, if you use the SPS, we should reduce 10 or 150 degrees the temperature. But about the reduction of temperature with SPS, you should take care, because it's not totally true. It depends where you measure and what different properties. Then okay, there are short sintering times is clear and the microstructure is modified, but the reduction of the temperature is not clear, because you measure not directly in your powder, you measure on the surface of the graphite tool, and then for some materials it's true, but for others it's not. Okay, and well, I don't know if you remember Monday, the first presentation was controlling the SPS, the current through our powder, and then we can modify. And in this case, we observed that the temperature by modeling was only a difference of 5 degrees. Okay, but well, always in the literature, I really like to mention that it's a reduction of temperature. Yeah? And well, here one of the most typical materials as to the zirconium diboride in order to increase the oxidation resistance, because as I told you at the beginning, this is one of the critical factors of this material. They have really high melting point, but the oxidation resistance is relatively poor, okay? Then the people normally use, well, different silicides, but the most characteristic is the molybdenum silicide. This one, for example, the zirconium, like it's zirconium diboride, will be great if you add zirconium silicides in order to reduce the impurities, but well, it has lowest melting point, okay? And if you want really just thinking in high, well, in the melting point, then you should use the wolframium even when it is so expensive. And well, just to put few examples as you see in the table, or pressureless sintering, or hot press, or spark plasma sintering, about densities and so on. Obviously, once that we have incorporated up to 20%, that is so much, okay, we can obtain relative densities, or well, practically full densification at relative low temperature for ultra high temperature ceramics. But then you should take care, because this material will be in your final material, okay? And well, here just a couple of examples. Depend which material we use. These silicides have sintering additives. Well, it will be the onset of the densification at lower temperature, and we'll find practically the full densification even close to 2000 degrees, but even here less than 1600, that is a really low temperature. And here, well, a couple of examples of the microstructure, because at the end is that it's important. I will show you later more microstructure, even directly from our work. This is from the literature. Using different sintering additives, but typically when you add a liquid phase, that at the end that you will add you will have, is spherical particles, okay? Because you see here that is all this liquid. And now probably the most interested material, that is this zirconium diboride containing silicon carbide particles, or a really recent research, even less than 5 years, containing silicon carbide fibers from one group from Italy. Okay. In that case, well, also they improve the oxidation resistance, but the idea to add the silicon carbide is to improve the strength. Well, and here I also put it, the oxidation resistance of your material. Okay. Practically all the work that you will see in the literature about ultra high temperature ceramics are in zirconium diboride that I mentioned, but also about the effect of the silicon carbide particles. Okay, it depends on, as usual, in several parameters: size, shape, content, how they are, the aggregation of also the impurities, agglomerations, and well, as I mentioned a couple of seconds before, recently, but it means even less than 5 years. I think it's a couple of years. This group in Dileta city in Italy, and other people, Monteverde, and people from Italy, they produce a really nice works on papers. They incorporate finally these silicon carbide whiskers, or even fibers, to improve the fracture toughness that we will see in the last part of the presentation. That is one of the main problems of these materials. Okay, and well, just here that also the silicon carbide improves some properties, but also helps the densification. And well, just here a few examples about the maximal temperature that is reduced in comparison with the normally 2000 degrees and so on that is required. Okay. Well, more densification, the relative density as a function of temperature for this silicon carbide. I think we are more interested in the properties than now in the densification, but well, obviously, if you increase your content in silicon carbide, this onset of the densification, the starting of the densification, will be a lower temperatures. Okay. And here a couple of microstructure, because of course it's not only, it's like we talked the other day. Okay, what is your limit? Then add no silicon carbide. But okay, depend what you want. I told you, depend the properties that you are looking for. If you add, for example, 20 volume% of silicon carbide, you will have this microstructure. If you just only add 5, you have this one. It's totally different. Here the grains are larger than here, and depend the properties that you are looking for. Maybe you are more interested in one or the other, okay? Because this one, as you see here, are sintered at under the same conditions, okay? At this maximal temperature. The thing, just to mention, of course, I don't want to talk about the sintering in general of ceramics, but if you add these small particles that you reduce or hinder, let's say hinder the grain boundary migration, and then if you have many, your particles normally are smaller, okay? That also helps the densification, because of course, as I mentioned, if you have smaller particles, they have more energy on the surface and then are easier to densify. Yeah. Well, now finally the mechanical properties. About that, I think even this table, I put only the first part of the table, but I think it continues and continues because this is that everybody study at the end. The mechanical properties of the zirconium diboride, but not only the monolithic, because then if not it's more or less clear, is with all the sintering additives or second phases that we want to add, okay? Then there are practically all the values that you want, but we'll try to summarize them, okay? As you see, the grain size, well, normally it's not higher than 10 or 20, even when you see here 20, but all of them are even less than 10. Elastic modulus of these materials, they are really stiff, stiff materials. Sorry, I start to be a little bit sick. And also, well, the hardness. The hardness is critical for this material. They are really hard materials, okay? And this is important for the tribological properties. Here maybe you see just 9, but this is because the relative density of this material is low. But when the zirconium diboride is relative close to the full densification, the hardness is quite high. Okay, even you see here close to 24, depend obviously in the grain size. However, and for that depends what kind of second phase you add, it will be decreased. But here is the main problem of the zirconium diboride, the fracture toughness, okay? As always in ceramics, the fracture toughness is a problem. We talk so much about that. Yeah, it's quite low. Even, well, this value is 5 even for a relative density of 90. We will check the reference, but typically it's less than 4, okay? And well, the flexural strength is good, but probably not enough. Anyway, these one are at room temperature, and the good response of these materials is at high temperature, okay? And well, as you see here, depend of course of the porosity and the sintering additive that you add. And then, well, I just want to plot you why it's so important to have the full densification of this material, because obviously you see a decrease of the elastic modulus, a function of porosity, and of course about the flexural strength. No, sorry, this is with the grain side, but obviously the flexural strength also decrease a lot with the porosity, okay? If we analyze now the flexural strength at room temperature, also, as I mentioned at the beginning, depend your technique, you can tailor your final microstructure, and you will have this tendency. For that, several people is trying to looking for this nanoscale of the zirconium diboride, but it's quite hard by the higher temperatures, okay? And well, now, as I told you, the most interested material is the zirconium diboride containing silicon carbide materials, and well, here more and more data, okay? I just want to show a little bit about that. The good part is when we incorporate silicon carbide, we will reduce the grain size for raw material, then will be more in that area, and the monolithic materials more maybe in that point, okay? The elastic modulus, we keep it in these values, really high, stiff material, also the hardness, and we increase a bit the fracture toughness. Probably it's not enough for some applications, but well, it's that we talked yesterday. It's an increase maybe of 50% or 40%. Maybe it's not enough, depend the properties, but if your material doesn't suffer a lot of mechanical stresses, it can work, okay. And well, as I told you, they depend about the size, well, of your material, but also about the dispersion of your silicon carbide. If you want to add the highest amount of silicon carbide possible, these phases will put together, and always that you have agglomeration, of course, will be a decrease of your properties. Here is plot the flexural strength, but all the properties are controlled obviously by the defects, and if you have a defect because you have a bad distribution of your silicon carbide particles within the zirconium diboride, your material will drop, okay? That is so here. Well, through different investigations, they observed that there is a threshold in this flexural strength that it drops when your cluster size is between 10 and 15, okay? Then you cannot add the silicon carbide as you want. It should be dispersed and with the amount that is required. And well, more and more properties. The flexural strength, again, we talk about why you not add more and more silicon carbide. Here, for example, the maximal content is 30%. There are not more improvement. Once that the percolation is achieved, the improvement is stopped, or for example, in that case, even is decreased. It increased, but at the end decreased. That again, depend your properties. You should think about that. And here that I mentioned, the fracture toughness, here it's a graph, and I think it's easier to see as a function of the silicon carbide content. Here is the monolithic materials. As I mentioned, well, there are some words that has like 5 or 6, but in general it's always lower than 4. With your silicon carbide increase always, but well, the improvement maybe is 50% or 40%, different percent, but the thing is that at the end it's difficult to overpass this value of 6. The improvement of 50% is still too low for some application. You need to change. So. Okay, and here is one example, okay, of the microstructure of our materials. These gray areas, okay, correspond with the zirconium diboride grains. As you see, well, this one is 5 microns, is less than 10 microns, and the other phase, the dark phase, correspond with the silicon carbide particles, okay. And here is the analysis of one crack. If we analyze, for example, here, and this is the problem and why zirconium diboride has a low fracture toughness, when the crack goes, I mean, they go directly. It's a transgranular fracture mode. Then the crack, I mean, it continue and continue. Nothing stop it. Okay. However, when we have close silicon carbide particles, like here or here, they start to be at least intergranular, and the crack is deflected. Okay. The effect is not so much because here the particles are really small and the energy, this one is quite small, but at least you improve a bit your fracture toughness. For that, that's the idea, obviously, to incorporate the silicon carbide fibers in order to do a higher deflection. But even with that, the increase of the fracture toughness is not so high. Well, that is exactly that I put here. But even with that, as you see, the crack continue and continue. And well, then, like this is a problem, as usual, and we are talking all the time about that. The idea is to add other phases to improve the mechanical properties in general, but especially the fracture toughness. Problem, if you improve some properties, other normally decrease. For example, is the case of the elastic modulus. Well, it decreases as a function of other additives, okay? Well, just to mention, okay, it decreases, for example, if you add this zirconium silicon, okay, decrease a lot. With this one, practically it doesn't decrease, and again, the good part is this zirconium diboride silicon carbide, and again, this is the reason why it's the most used materials. Okay? Again, different materials, well, different properties. Will not go in detail about that, only mention that here the fracture toughness is increased a little bit, keeping a good values for the flexural strength, okay? Always that we are talking, of course, in terms of really high dense material. And as you see, well, values, and a lot of people researching about that, about the mechanical properties, but well, a lot of efforts are done here. As you see, probably we need another strategies. Yeah, it doesn't go really farther. And again, well, we can increase, for example, the flexural strength, because, for example, this size, as I mentioned, improves the sinterability, and well, it's one of the most uses, because at the end the properties are not really affected. For example, you see here are relatively flat, or here this one even increase, or if they decrease just a bit. Again, the fracture toughness, they can increase, but even you see this word, it's not clear what is the tendency, or it decrease, or suddenly it increase. It's not clear, but the important thing to remember is that we are always in these values around 4, 5, and well, I think we need a better improvement, and at least at the moment it's only this silicon carbide, okay? But well, as you see, even with the silicon carbide, for example, the flexural strength decrease, as I told you, even with the fracture toughness increase, but depend the values. I mean, here decrease or keep constant, and it's not really clear. And then, well, now I think we start ready to talk about the temperature materials. I mean, the response at high temperature, because this is always the problem. All the ceramics material, and obviously all the other materials, when you increase the temperature, you suffer a drop of your material, or even it can be melted. As you see here, the elastic modulus quite high at room temperature, but it starts to decrease and decrease. Up to 1200, it's still so high, even when you say this decrease, but this for 400, that is quite high. But from this temperature around 1600, the decrease it's a big problem, okay? But for that, I would like to remember, even when you see this drop at 1300, like here, keep around 400 gigapascals. It's a really good response with really high elastic modulus. Well, what are the effects? As typically, when you increase the temperature, you start to suffer the softening of the grain boundary faces. You always have impurities and different layers that you produce. Yesterday we talked about these nanotubes acting as grain boundary sliding, because they were between the two grains and they can move. With the temperature is relative in that way. At high temperature, like the really nano layer that is between them is start to be softening, the grains can move, and then you decrease your properties, and of course start the creep of your material that is so critical, okay? And I think I have a few graphs about the creep resistance. And again, well, the flexural strength to be a ceramic, this is quite high at room temperature, and well, we see that they keep relative well until temperature again around 1600. That is a really high temperature. Again, we can see here, okay? After that, well, it's a decrease, and it's around 200. It's a drop, and even more drop. But here at that point, we are talking about more than 2000 degrees. Okay, it's a really high temperature. If, for example, yesterday we talked about the thermal barrier coatings that we want that our plane works several hours, several days, months. But for this kind of application, if we want to go to this temperature, for example, to go out the earth or for the reentry of the vehicles, we are talking about seconds or minutes, okay? Then we just need to, let's say, survive for a few moments, okay? But again, the problem with the fracture toughness also decrease, but well, at least at really high temperatures they keep it's maintained. It's low all the time, but at least it's not a big drop. And we see that the temperatures are quite high, even at 2000. Well, we are between 3 and 4, and normally for the monolithic, well, here was 4.5, but as we see on the others are normally like here, then it's more or less kept the resistance, the fracture toughness in that case. And now the other important point, the oxidation resistance. If we want to use the materials, maybe where we locate our materials, they don't suffer a lot of mechanical stresses, but practically sure that we will need that our material present a high oxidation resistance, and for that this is a totally critical point of the ultra high temperature ceramics. They resist high temperatures, but the oxidation well, is not good, and of course it's worse and worse when the temperature is increased, okay, mainly through these reactions. For example, our zirconium diboride is combined with oxygen, and then we'll form our zirconia and this boria that we melt. And as we see here, and obviously also in that case, this free energy is negative, then this process is promoted, okay? But well, as I told you, this one at low temperatures, this boria, and during its liquids, it helps to protect our material. I think I have a couple of materials about that. I think so. Yeah, it's exactly here. Okay. Here we have our zirconium diboride inert at just 900 degrees. Let's say just because we want to use a really high temperature during 4 hours. And that we have is our zirconium diboride without any reaction, because the part of the material that reacts is that one. This layer corresponds with a porous zirconium oxide, because we produce this reaction. Wait. And that we have here is this layer of boria, okay, that it protects because it liquids. But there are two problems, but step by step. This boria is on the surface, is liquid, and then avoids that the oxygen can penetrate through this zirconia oxide through the pores and continue oxidize and oxidize again our material. There are only one problem. This one is liquid, okay, and if we want to go this Match 5 or these really nice vehicles that I put you in the presentation, will be a lot of flux of gases, of course, and if you have a liquid protection, okay, probably is gone. But anyway, they protect, and we will talk later how to really resolve this problem. But what is the problem? This is just 900. If we want to further temperatures, for example 1500 and just 2 hours, we see it's a totally different microstructure. This one, all of it, is the porous zirconium oxide, okay? All material practically is gone. Why? Because this boria that was liquid and helps to protect, at this temperature evaporates, okay? Then if we don't have our boria, we just have our zirconia that are porous, because here was the boria and it's gone, and then the oxygen can penetrates and reacting with our zirconium diboride. Therefore, if we want to use this kind of material, we need our environmental barrier coating, as I told you, or improve these layers against the oxidation to avoid exactly that one, okay? And here is one scheme how it works. Our zirconium diboride, or zirconia that is porous, and it can be filled by this boria, protected against the oxygen, okay? This is quite good. Of course, depends of the partial pressure of oxygen and different things, but well, in general, at relative intermediate temperature, we have our boria protected our material and works quite well if it's a low temperature, okay? Problem, if we go to higher temperatures, really high, our boria is gone, and we have a porous structure where our oxygen penetrate, okay? Then, how to improve this one, because always we should look for solution. For example, in the case is adding silicon carbide. I think verily, I told you the other days, silica can protect, okay, but the volatility is low and so on. Then the best option, for example, if you are silicon carbide, is that this silicate glass that you form is a borosilicate glass. Then it has higher viscosity, and the point that it volatilizes it's lower. Then that we have here, even with the oxidation is severe, is all porous structure based on zirconia, and this borosilicate glass that you see even at this temperature, in that case was 1500, and here is even further, 1627 degree for 100 minutes. It's still protected by this liquid phase, okay? This glass is not like a liquid exactly, but well, it's a glass that is made and is filling all the pores in order to avoid the oxidation. This is one solution that is found until that. Even your material at the end will be oxidized, but at least is reduced, okay? And well, just here one comment about that, your zirconium with the silicon carbide that survive, the silica, of course you suffer the oxidation of the silicon carbide, and for that is boron silicon gases that are protected, and here the reaction again is this protected of the silica or the borosilicate glasses, okay? Well, here just the range of temperatures that it works, but I think it's not important that you should remember that this glass liquid protection that it works, but in general we should improve it, especially because it's a liquid, okay? And for that is that I think quite intelligent idea, okay? That they mostly developed in that group in London. If you remember yesterday, we were talking about a new materials for TVCs that was called zirconates, gadolinium zirconates. Maybe you remember, it was only yesterday, okay? Try to do the effort. Then that here that we want to do is promote instead this glass to promote in situ the gadolinium zirconate, okay? Then that they add is to add to the silicon carbide also 10% of the gadolinium oxide, and this is that I told you at the beginning. Just think, because then you can find some solutions, okay? They add this gadolinium oxide in order to promote these reactions. When the zirconium that is, or porous structure that is formed, reacts with the gadolinium for this material that has a really good response against the oxidation, okay? And then that we will observe in the next picture is like that, okay? For the monolithic materials that we had is our zirconium diboride with the porous zirconium oxide. Then all the oxygen can penetrate and react with the zirconium diboride. If we incorporate the silicon carbide, we have seen that, okay, we have our porous materials, but there are a borosilicate glass or a silica liquid that is protecting our material, and then the penetration is lower. But here that they produce through the addition of this oxide is a really large dense layer, but that at the end is dense, then can survive just a small part of the porous, and at the end our material, okay? The rotation is larger because here is, for example, for these cases was 250 microns, but the good part is that this one is dense, and if we are really thinking in final properties or in a final components, a liquid protection is not good enough. I mean, we need to produce something dense, okay? And well, here is a couple of pictures for the publication, okay? That here, well, this part is this gadolinium zirconate that is formed. You see that is a lot of porosity and so on when they use the EDX to characterize, and it's larger as we saw here, but at least it's dense, okay? And this is a really good improvement. But what was the problem in that case? That this gadolinium that they introduced in all the material, well, decreased the other properties, as you see. And then, well, I had this idea that is to promote the formation of these gadolinium zirconates only on the surface. and here I want to do a break, is that I told you, now you are in the university and you have several opportunities, different agencies that supply a lot of money for students. This is just one that I had. I applied for that, and they give me the opportunity to go to London to do it. I mean, you are in the right moment right now, and in Europe there are a lot of things. Maybe now in Spain is a little bit more stopped now for the crisis and so on, but in Europe there are a lot of possibility for people like you, for young people, to have different ideas that can work or cannot. In that moment, the idea that well, I have, or we have in my group, it's okay if this work, because we want to generate a dense layer, but it's affected the properties, why not have this gadolinium only on the surface? Then we did it in 3 different steps. We have our zirconium silicon carbide materials, totally dense, and through laser ablation we did small cavities, okay, on the surface that it processes in seconds, okay, the equipment do it so fast. After that, we fill these small cavities with gadolinium oxide, okay, with some gadolinium powder. We fill that one, and when the process, and when the material is at high temperature, the glass that is from on the surface will react with our gadolinium, forming just on the surface a dense layer, and then our material will remain just the zirconium with the silicon carbide, and they keep these properties, okay? And then to do that, of course, I divide by different steps. The first thing, I think this picture I put you a few times. First, develop our zirconium diboride with the silicon carbide particles, okay? We densify at 2000 degrees, I think so, in the SPS for sure, and then we obtain a dense material where there are a few pores, but it was 99.5, something like that, the density. Then we obtain our dense materials. And as I told you, we did small cavities in a pattern with a surface engineering by ultra-fast laser ablation in collaboration with other group. Some of you during this day told me that you are interested in some surface treatment. For example, this one is one of the possibilities. Advantage of these techniques: every cavity what we do it well has a pulse of just 8 picoseconds. I mean, it's really fast to do it, and well with different properties. But the important thing is that it's just question of minutes to have in a sample that it's quite easy to really process large over large specimens, okay? And they look like that, okay? The thing is that we didn't know about the distance of these cavities that we require, okay? Then we thought, okay, we can do partners where between the centers of 2 cavities, the distance is 10 microns or 20 microns, or that one with 50 microns, okay? But then these three patterns, sorry. And here that we see, I think I have, yeah, okay. Well, it's our cavities, and we go more in detail, and well, we can observe different things, but I think it's easier, yeah, exactly, to show here. But well, as you see, these cavities are formed, and all of them has a diameter close to 10 microns, okay? Just here that we need to control is the distance, because we didn't know how is the amount of gadolinium that we should incorporate. But if we analyze, because here obviously is where the laser impact, and they make the ablation, okay? That is here, is the laser spot. But after that, we also have one part about molten material. Even you can see here, looks like if like a molten material was cooling down, okay? And other areas that we saw, this is some of the distortion of the beam that also impact here. In some of them you can see here, but in others not, okay? For example, in that one, no. And the important thing, for example, is that in zirconium diboride it works perfectly, but also in the silicon carbide particles. And that is also critical, or quite important, is that there are no micro cracks processed from this process. That we did also to characterize the depth of the cavity, because okay, we can measure the thickness, but we don't know how is the depth. We did a FIF, we cut it and analyzed the cross section, and was like that. And then the depth is like 10 microns. And well, just to mention there are different zones, and this one corresponds with the molten of the materials, but really close as here there are not reaction, okay, with the process. And then the second step, that was to fill in the cavities with that process. Well, there are different possibilities, and we thought, okay, how we can do it, but of course, if we want really to transfer that, it should be cheap and fast. And then was a really easy process. We just put our powder in dry. We try also with different suspensions, but in dry it also works. We put on the top of our material the powder, and like I explained in the other processing methods, we just pass several times like a screen printing, but without suspension in a dry powder, and then we observed that all our powder, all our cavities were coated with this powder, okay. And when we did the EDS, of course, we observed that this one was the gadolinium oxide, and if we were really in detail about this one, we see that it's our nano powder of gadolinium, okay. And then that we did is the oxidation of the material, okay. But first, the monolithic material, just the zirconium diboride with the silicon carbide, but without any treatment. And as I told you during this presentation, that was at the beginning more theoretical, here is one example. Well, the zirconium diboride, of course, oxidized, and for this zirconia, amboria, and the silica reacts, and is the formation of the borosilicate glass at temperature higher than 1200, and here is clearly divided, okay. In this part, we can see of unreacted zirconium silicon carbide composites, no reaction, everything is good. Here, this part corresponds with the zirconia and with some glass that is filling the pores, and all this glass is the borosilicate glass that protect our material. It's at 1600 degrees, okay. But as you see, it's a really thick layer of a glass, okay. It's at the end, it's liquid. It's a glass. But then that we want, as I told you, is that this zirconia react with the gadolinium oxide that we have incorporated to form this gadolinium zirconate, or on the other hand, that can happen is that our gadolinium instead react with the zirconium oxide, react with the borosilicate glass, with the silica and the boron. That then we will form a gadolinium silicate glass. And well, here are the examples, okay. I hope I don't lose you. Here is with 10 microns of cavity, 20 microns of cavity, 50 microns of cavity. I forget to mention about that, just to compare. Well, we did deep coatings in case that for comparison, if we need this really laser treatment, or can be done just by deep coating. But okay, focus just on these three. That we observe, for example, is this 10 microns cavity, is this borosilicate glass. Okay, was not a void. We still have it. This gadolinium zirconate was maybe not formed, but that is clear is that it's totally decreased. I mean, here we have, and I think the magnification is the same, all this thick layer, and here is really thin, and even we observe here or particles. For 20 microns, also we observe the same. The content of liquid is low, but if we go to the 50 microns, the content of liquid is so high. I mean, we practically don't observe any advantage to add that one, because that we conclude is that obviously our cavities should be closer, like these two ones. Okay, and well, as I mentioned here, we separate here the porosity and glass, but the important thing is to remark is this small part. And here, one example, to put together and easy to compare at the same magnification for the monolithic materials with the 20 microns that we observe as the optimum distance. Well, is the reduction of this silica glass even when we have our own the same thickness of the zirconium oxide. Unfortunately, we cannot promote the first idea, that was the gadolinium zirconate. Just we reduce this amount of liquid, but okay, well, maybe it requires more and more work on that, because I think we are going in the correct direction. Okay, but at least that we reduce is this liquid phase. And well, just we characterize, I don't know if you can see really well the maths here, the resolution is better. Well, we characterize, and that we finally form is not any gadolinium zirconate, but we change the viscosity of this borosilicate glass that now with incorporation of the gadolinium is really, really high viscous, and then protects the oxidation of the surface. And just to finish, what is really the status if we want to process really hot structure based on ultra high temperature ceramics? As I told you, they want to use it for the thermal protection systems when the vehicles go and out from the Earth atmosphere. And then, well, there are two categories, the possibilities for this thermal protection system, if it's ablative or you can reuse and so on. But okay, I think it's better if we go directly through that situation. Well, here is the research in the last 10 years, okay, going in that direction, mainly, as I told you, done by this Italian group that are quite good, okay. As you see, there is already a start to process on some pieces to be really used on that. Normally they know what is really the temperature is protected, and as you see, well, just in 10 years they are doing different shapes and use, for example, in that case, in different rockets, always, well, with metals and so on, but that the core is this ultra high temperature ceramics. And here also one example, for example, the pieces that they are producing now, where this here, that is the critical part for in terms of temperature, is this ultra high temperature ceramics, is zirconium diboride, or here different materials. Here, for example, you see this zirconium silicon carbide on different parts, okay, but that you see they already produce large pieces that are used, okay. Well, I think that's all. Yeah. Thank you very much.
Any question? No? Well, we have time for a coffee.
This one was a little long, but it's just another presentation, and you are free, don't worry. I don't know, 20, something like that? Or even more?
15 minutes?
Yeah, 15 minutes. Yeah.
It's okay.